Welcome to Module 5. In this module, we're going to be looking at production of power from heat. So our goals in this unit will be to analyze the material energy and entropy balances for multi-unit cycles. So we want to recognize the purpose of simple and modified Rankine heat engines and appreciate the role that each of the unit operations plays in this process. We want to then be able to propose designs for a Rankine heat engine that will meet a specific goal and operate within given constraints, maybe a maximum temperature pressure. We want to also be able to compare and evaluate process designs that use efficiency as a benchmark. So, power systems. We've sort of addressed this before, but kind of as a recap, the purpose of a power system is to produce power. And we measure the performance typically using a thermal efficiency. Now, for any power cycle, that thermal efficiency is the net work divided by the heat input to that cycle. The maximum value is defined by a Carnot cycle, and this can be computed using the temperatures as absolute temperatures, so degrees Kelvin, degrees Rankine, and that would be 1 minus the ratio of TL over TH. So this is always going to be a quantity less than 1, but more than 0. Earlier in the book, we've looked at models of the way that real cycles produce power. The Rankine cycle is a very common model as a starting point for how we can do this. Typically, when these are done, they are done with steam. The steam might be heated by coal. There are several coal plants in, say, Oklahoma. They might be heated using natural gas in other parts of the country. But the steam is the operating fluid in this cycle. And generally what we think of is that we think of starting it just as a pool of liquid water. Okay? I'm going to take that liquid at a low pressure and pump it to a high pressure. Now, ideally this pump will be insulated, so Q will be 0. It's going to require some work input. Once it's at a high pressure, I now want to get it to a high temperature. So I'm going to bring heat into the system and boil it until I've reached a vapor. So that final temperature will either be the saturation temperature if I just barely boil it, or I'll superheat it. Once it's at this high temperature and pressure, I'm going to run it through a turbine, and that's going to produce power. This is the most critical step of a Rankine cycle. So this vapor is going to enter the turbine, and it's going to be depleted of all of that high energy that it came in with. So the pressure is going to drop, the enthalpy will drop, and work will be performed. And then finally, I need to return it to the initial state. So I'm going to condense it back to that liquid state, and it'll go back into the pump, boiler, turbine, repeated ad nauseum. We can draw pictures of it. Every textbook has their own style of how they draw it, but basically it looks something like this. So I'm going to start by bringing a fluid in as a pump. It's going to go to a higher pressure, go through the boiler or vaporizer. It's going to come out at a high temperature and pressure into the turbine or expander, where it's going to use the energy to become power and come out in a low energy state at a low pressure, but still as a vapor, and then go into the condenser and return the cycle. I can graph this on PV or TS diagrams, are the two most common, but this is what a TS diagram for an ideal cycle would look like. So the pump, whether it's perfectly efficient, it's ideal or not, I'm not going to see too huge of a change on this side of my TS diagram. It's going to then increase to a high entropy as well as enthalpy state after the boiler. It's going to come through the turbine. Ideally, it's going to stay at constant entropy because it was reversible and adiabatic, and then return to the original state. Now, the fact that a turbine and the pump also, but to a lesser extent, are not perfectly reversible means that I will not get the work in or out of these things that I had expected. So the actual drawing is more like the one that's the solid line shown here. Now the first and second law, well, it seems like it's a closed system, right? Because I'm going to keep the same material flowing through there. But each unit is going to be a steady state device. So I'm going to model these using the steady state form of the first law and the second law. So these are the ones summarized here. And then most of my equipment is going to be pretty much the same ones all the time: pumps, boilers, condensers, turbines. And so I can then come up with simplified forms of these laws. So typically what I can say is about the pump is that Q is 0. I will try to insulate my pumps. Now, work is going to be the enthalpy change from the inlet to the exit. That's great, but the problem is that this is going from being typically a saturated liquid to a compressed liquid. And that's not really a problem, it's just that I don't usually have data for that. So if I can't find the enthalpy at the inlet and the exit, I need another way. And when we reviewed the first and second law for various devices, for pumps, we saw that V delta P was a good approximation if there's very little change in kinetic and potential energy. So V delta P is a way of approximating the work. That actually can allow me to calculate the exit enthalpy from the pump. Now this only works for liquids going through a steady state process. Next I'll take it through the boiler. There will be an enthalpy change, but no kinetic or potential energy. There's no moving parts, so work is 0. So therefore the heat required in the boiler will simply be the difference in the enthalpies from inlet to exit. The turbine is going to produce work, but will be insulated so that there's no heat loss. So I'm going to get the H at the inlet to the turbine minus the exit is going to be my work. This will be a positive number being produced. Okay. Now here the material is going to be a vapor. For vapors I cannot use V delta P. That only works if V is constant. And in a vapor, V is constantly changing. So I just need to use the delta H. Then I'm going to send it through a condenser, similar mathematically to the condenser, but the energy level will go down. Heat will be lost from the system in the condenser. So these examples, I am going to go through them very fast. I will, in the learning management software for the course, I will include the Excel files that I'm going to be showing you so that you can take these at a more reasonable pace on your own. But I just want to kind of very quickly show you how the Rankine cycle calculations can be done and the things that people do to improve the basic Rankine cycle. So here we have one. I'm using a Rankine cycle with refrigerant 134A as the working fluid. You'll probably need to find data in a textbook, but you can also find these online. Okay. Saturated R134A is going to leave the boiler at 85 degrees C, and the condenser is going to operate at 40 degrees C. So I have this high temperature and this low temperature for the cycle. We want to find the work of the pump and the turbine, and we want to find the heat transfer at the boiler and condenser, and use those to find the thermal efficiency. So I use data from Sontag, Borgnacki, and Ben Weiland's Thermo text. I found the data. So temperature and the quality, right? It was a saturated fluid. Leaves the boiler, so I know that at the exit to the boiler, state 3, and I know that the pump is going to be at a temperature of 40 degrees C, and I assume that the saturated liquid is going into the pump. So I'm going to start with temperature and the quality at state 1 and at state 3. Those are given. Based on that, I can look up the other properties. Now, what about the other stuff? Well, I know that the boiler is going to operate at constant pressure. So the pressure 2 and pressure 3 will be constant, and the pressure 1 and 4 will be constant because the condenser also operates at a constant pressure. Now, I don't know what the other states are from the given information. However, the turbine, I can assume if this is a reversible turbine, that the entropy across the turbine is going to be constant. So the entropy of state 3 and the entropy of state 4 will be the same. I also can assume that about the pump, so entropy 1 and entropy 2 are the same, but sadly that doesn't really help me get the H. But remember, for the pump, I can say V delta P is the work and use that to calculate H2. Doing that, calculating the various work inputs, so these are all specific work and specific heat in this case. I calculated the net work, the boiler heat transfer, the condenser heat transfer, and found that this cycle was 10% efficient. Again, you'll want to pause the video, go through and review this on your own to make sure you really do understand this. So we're going to, in the next video, start looking at what happens if I change the operating conditions. So we'll pause the video here.